Yes, here we are. It's the physics video lecture, fluid mechanics video lecture 2. And we had ended with full derivation of the equations of motion. I guess I'll start with those again. First of all, from the conservation of mass, we end up with the continuity equation, d rho dt plus divergence rho times v equals 0. V is, of course, the thing we're interested in finding, velocity field. Then from Newton's law just applied to an imagined droplet of fluid within the entire mass of fluid gives us the following. The left side of Newton's law is an acceleration, but because we're in the field as opposed to pursuing that droplet, we have this added term here, v dot gradient applied to the vector v minus 1 over rho gradient of the pressure. So this was the acceleration equals force over mass expression here. And then finally, I'm just going to write entropy equals constant. These are equations with no energy dissipation, so it's an ideal fluid. Good. And plus boundary conditions, v dot n hat equals 0 at a surface. Now, this is ideal fluid. A real fluid, we would say, so again, we'll note this. For a real fluid, things are more difficult. V is identically equal to 0 at a solid surface. Okay, so there's a difference. This dot product means that, for example, we could have our surface here. There's the surface normal, and so we've got some fluid flow, as we'll use blue for it. We've got some fluid streaming this way. There's our vector field, or field lines, if you will. But because the condition is this dot product, we're still allowed to have a non-vanishing tangential component, right? Because that dot product is 0. So we're still allowed to have it sliding along the surface. I mentioned that last time. These are really technical aspects, by the way. We're not going to impose these for some time. But yeah, there's the situation. This can still be non-zero. Of course, its normal component is 0. Okay, what we're going to do, right here next, we're going to take an incompressible fluid, so with the incompressible fluid, rho is equal to constant, and our first equation, equation 1, turns into divergence of v equals 0. Actually, I wanted to have the external field in here as well. G just represents the external field. It's usually gravity, but we had that last time as well. Okay, so we put that in there. So incompressible fluid, we have divergence of v equals 0. Also, let's now assume the hydrostatic case. Well, I'll send this board up, and then we'll talk about hydrostatics. Good. So incompressible fluid, the divergence of v is equal to 0. That comes from here. And now what happens to this equation? Okay, so hydrostatics. We're going to start out pretty basic. Hydrostatics is when the velocity is identically equal to 0. Situate, the water's just in, or the fluid is just in equilibrium and at rest. So V equals 0, and now we have the right side of this equation. So we have, and gradient P is equal to rho times G. Gradient of P is equal to rho times G, and G is a vector. I said that's that external field. And what we want to do is solve this differential equation to talk about pressure, depth, Archimedes Principle, and those things that we want to review. So, the example is we've got our positive z-axis and g vector is equal to minus g k hat. That's good enough. X and y are in the plane here. So now we can write this out. We have dp dx is 0, dp dy is equal to 0, and dp dz is equal to minus rho times g. So this can immediately be integrated up. P is equal to P0 minus rho gz. So that's the pressure depth formula if we were at some surface here. I'll call this surface Z equals 0, where we have atmosphere above it and water beneath it. Water's always good. Then this would be the atmospheric pressure, and that would be minus rho gz. From Z equals 0 would be at the atmospheric pressure. I'm just going to put here, we can also write P equals P0 plus rho GH, where H measures the depth. This is the way it is in our lower division textbooks often, okay? H is equal to the depth. But yeah, they're identical, and what is interesting is the pressure only depends on the depth and doesn't depend at all on the volume of your vessel or the width of your vessel. So here, let's go ahead and imagine we have a vessel here, we have water in it. This thing could be 10 times as wide. Pressure still just depends on the depth. This could, for example, be the wall of a dam. And then the pressure on that dam only depends on the depth, of the water, and it doesn't matter if it backs up 100 meters or 100 kilometers behind it, the pressure on the dam would still be the same thing. Which would actually make an interesting little assignment. Maybe I'll put that up right now, where you could find out what is the force, the total force due to water pressure on such a dam. In fact, why not? Let's go ahead and put this as an easy little task. Find force exerted on a dam by the water that's being held back. And in order to make this concrete, let's go ahead and do my best at some profile here. So here's our dam. Okay. And the water being held back back here. So we'll just label this thing. So the dam has a depth H, so from the water line down to the bottom would be H. And the width of it, we'll just say is W. It's going to be readable. There's the dam. The width of it is W here. And it has water. Water's being held back. So force is pressure times area, and here the pressure is just increasing with depth. So that shouldn't be that hard to do. A worthy little problem there. Find the force exerted on a dam by the water being held back. Good, that's a nice little problem. In fact, that's the kind of thing you leave several lines in your notes. You can probably just fit it right in there. Good, so there's our pressure depth formula. And what we want to do next is use this to derive Archimedes' principle. And the basic version of Archimedes' principle, it can be derived without major shenanigans, but we just go ahead and describe it. Archimedes principle. So the idea is that under some fluid, you have some object submerged. Okay, imagine you had some cylindrical object, and then all the forces due to the pressure horizontally are just going to cancel each other. But what you're going to have is a greater force on the bottom than you have at the top, simply due to the gradient in the pressure. Okay? And that net force, the difference of these two vectors, is going to give you your buoyancy force. So F net, so this is, I'll just say F2, F1. F2 minus F1 equals F buoyancy. So that's where it comes from. That is to say, if you didn't have, there's our Z direction again, if you had no gravitational field, then you wouldn't have a buoyancy force. So that's good to know. Let's do the integral, though. So we have on this object, say it's some arbitrarily shaped object, we have the net force is equal to the integral, and we're going to have a minus sign, aren't we? Yeah, we're going to have pressure D area, okay, like that. And since there's a volume here, volume V, that's the surface area of the volume. So in fact, this is the expression we had the other day in the first lecture, minus surface here, P dot N hat D area. Okay, so let's go ahead and just look at F net comma Z, or actually just X sub I hat. That will be the dot product of this expression with X sub I hat, X, Y, or Z. So we'll have minus integral here, P X sub I hat dotted into N hat D area. And we can use the divergence theorem equals integral the divergence of this vector d volume over this volume. Okay. But what we're going to find is, where do we have it? Yeah. Let's set this up. So now we need that identity again. I don't know if I assigned it last time. It'd be a good one for you guys to knock out, just to have it under your belt. So when we do the divergence of a scalar times a vector, find that that's either f times the divergence of the vector or a dotted into the gradient of the scalar. Okay. So in this case, our scalar is the pressure and our vector is the unit vector. So the divergence of that unit vector is of course 0 because it's a constant vector. So we're looking at this right here, and we'll have x of I dotted into the gradient of the pressure. Okay. So F net x of I hat is going to be minus the integral x of I hat dotted into the gradient of the pressure d volume. And the gradient of the pressure, remember, it only had an x component or a z component, so only one of these is going to be non-zero. So it's only going to be F net k hat direction, z direction, going to be minus, and then we're going to have gradient of p will be minus g, minus rho g, minus negative rho g, and then we'll have the integral, having pulled all that out, of the d volume over the volume. Minus signs cancel, and this is the buoyancy. I'll just write F sub buoyancy force is equal to rho g v. So that is the buoyancy force, and we should actually continue this because density times volume is of course a mass, and mass times g is a weight. That's why we say it's the weight of the displaced fluid. Weight of the displaced fluid. Right? And this density has nothing to do with the object. This density is the density of the surrounding fluid. Okay, there's our Archimedes Principle. Oops, that B belongs up here. Here's our Archimedes Principle. That's the buoyancy force. Weight of the displaced fluid. Good, let's do a couple of examples of this. Elementary but important. And yeah, we didn't need any parallel-sided walls or anything. This thing was just completely rigorous. Now, if you check your lower division physics textbook in the chapter on fluids, then you'd find a whole wealth of these types of problems to solve using Archimedes Principle. They're certainly interesting. So let's just do a couple of examples. We're going to do the iceberg, the hot air balloon, and then another interesting one. So first of all, the iceberg. Here in the water, we've got this submerged, the mass of the ice is submerged. You want to collide with this thing. And what we do is just apply Newton's law of equilibrium. So we've got mg pointing down, and we've got the buoyancy force pointing up. That's it. No, there aren't any other forces acting here. So what we have is buoyancy force minus mg. Buoyancy force minus mg equals 0. We've got the density of water, the volume that's only the submerged volume, so volume that's submerged times g, and that's going to be equal to, this mass is going to be the density of ice times the total volume times g. G is going to cancel. Oops, cancel the wrong one over here. G is going to cancel. And we could say, what's the ratio of the volume submerged to the total volume? That's going to be the ratio of density of ice to the density of water. And whatever that is, you look it up, it's roughly 9/10. So that's a good example. This other example I'll do as a problem. This is kind of a fun one. So imagine you have a beaker and it has a certain amount of water in it, and we're going to suspend an object here that's denser than water, and this is going to be hooked up to a scale. The scale's going to have a reading, and we're going to put this thing on another scale. This is some kind of kitchen scale, and this is also going to have a reading. So let's say mass of the beaker equals, I'm just going to do all 1 kilogram, and this is aluminum, equals 1 kilogram. Mass of the aluminum block equals 1 kilogram, and the mass of the water equals 1 kilogram. So this is the tension T. So actually, tension is being measured by the scale here, and this is the normal force. I'll call it N, and N's being measured by the scale here. That's a normal force on the beaker. A beaker, aluminum block. For the aluminum block, you're going to have to find the density of the aluminum. Mass of water, 1 kilogram. So the homework problem, find N, the normal force, and T, the tension. So that's just one of those problems that this problem can be used for other things as well. You could do the same setup to suspend a mystery object and find its density, right? You could turn it around. So I'm just saying find the tension reading and the normal force reading. If you knew those two readings, well, first of all, you know the sum of them is going to be 3 kilograms times 9.8 meters per second squared, right? 3G. The sum of them, but individually what they're going to be is going to depend on this substance. Okay, good. So those are some your basic buoyancy type of problems. Now, let me check the clock. Okay, perfect. So I have a more interesting problem as well. And what we're going to do, this is our hydrostatic equation. And before I do the more interesting problem, you can, like I said, you can look up other buoyancy problems in your book, in your undergrad physics books, just to see what the range of the interesting problems is. But I think we've covered it pretty nicely with these two examples. You can do hot air balloons or hot air balloons, helium balloons, that type of thing as well. Same principles. Okay, but the problem we want to talk about now is a hydrostatic problem of a gravitating fluid. So imagine you have a star or some kind of cosmic body or some kind of large body that's just being held into a spherical shape by gravity. And that's not uncommon. And we're going to use our simplifying assumptions of incompressibility and thermodynamic equilibrium we're gonna leave all temperature considerations out. So this would be the most basic astrophysical problem, a little too basic, but it's a good one. So we're going to do that. Yeah, I'll just send this up. I'll rewrite everything. So the problem is a gravitating body in equilibrium that takes on a spherical form, and we want to find out about its pressure depth formula. Right? The pressure depth formula that we have here with uniform gravity is just rho g h or minus rho g y, rho g z. But if we want to do this for a spherically symmetric body, it gets a little more interesting. Okay. Yeah, we'll start this one fresh. So the problem is, what's the pressure depth formula for a spherical gravitating body with an incompressible fluid? So once again, all this hydrostatics. We have the gradient of P is equal to 1 over rho, no, other way around. G is equal to 1 over rho gradient P. Because that's just the right side of Euler's equation. And we're also going to use rho is equal to constant. So find P of R for a spherical gravitating fluid. Total radius R, capital R. So there's our big fluid drop, radius R here. And we'll say that P of R is equal to 0, comma, for R greater than or equal to capital R. So you're out there in the vacuum of space, as it were. Okay, let's see how we're going to set this up. This is an interesting problem. And here's another interesting thing. We're going to know a limiting case, okay? Because the limiting case will be, say you're right at the surface of this thing, it's just as though you had your normal pressure depth formula. So the limiting case should be that dP dr evaluated at the surface should just be that minus rho times g. And g will be the gravitational acceleration that we know from studying gravity for, you know, an entire uniform density distribution. So for the total mass, same expression you have when all the mass is concentrated at the center. So that's the limiting case. So I was going to set this up or do most of it. I'll leave a few, at least some of the interesting stuff for you guys to do. We're going to find pressure, depth formula, and we know that limiting case dP dr will just be minus rho g, just with the same way dP dz was minus rho times g. So let's see how to begin. So first of all, we have to get an expression for g here, because this is now a field. It's not just some constant at the surface, it's a field throughout the entire thing here, and it's actually going to be g as r. So first, find g of r. And we did that in 105b, but I'm going to appeal to Gauss's law for electrostatics just to jog our memory of how we can do that. So recall Gauss electrostatics. And there we know that we have integral of E dot n hat dA, that was that flux integral of the boundary of some volume. And of course we're thinking spheres right now, so it's all going to be simple. Is equal to Q enclosed over epsilon naught. And the law that we have for the field, it's Q over, for a point charge now, 4 pi epsilon naught r squared r hat. So that's how it works with Gauss's law. So what about for gravity? We want to do the gravitational version of this, make up a little more room. So what about gravity? In case we hadn't memorized this, we'd like to derive everything. You know, they're both 1 over r squared laws. That's why we can do this. Okay? They're both 1 over r squared laws. So for gravity, we're going to have g dot n hat d area around our volume. Okay. And then let's write down the gravitational law here first. You know, we have g for the point mass is equal to minus g m enclosed over r squared r hat. So there, just by making that substitution, the identification, we get the minus sign, we get the extra 4 pi, okay? Epsilon naught cancels up there. So it turns into minus 4 pi g m enclosed. So what we want to have is minus 4 pi g integral rho d volume over this volume. So this is what we're after right here. Okay. because the M enclosed is integral density of D volume. Okay. So there's that. That's just a way to jog your memory if you'd forgotten this form of it. You could go the other way around too. If you remembered the gravity, you could get your electrostatic. Now, what we're going to do here is take the divergence theorem here. So now we have integral divergence of G, D volume. In fact, I'm going to do two steps at once. Over the volume. This one's got the minus sign. I'm going to bring it with the plus 4 pi G rho. Okay. D volume equals 0. And because this volume is just chosen arbitrarily, we require the integrand to vanish, or we conclude that the integrand vanishes. So we have divergence of G equals minus 4 pi G rho. Okay, so this is well, we're almost there, but because we do know something about G in terms of the pressure. So G is equal to gradient pressure over rho. So we immediately write divergence of gradient of pressure divided by rho is equal to minus 4 pi G rho. And we're going to go one more and say that rho is constant. And then we'll have a del squared. And this is our equation. Del squared pressure equals minus 4 pi G density squared. Okay, since we have no temperature involved in here and we have incompressibility, this isn't going to be some star. Okay, astrophysics is a little more complicated than this, but we do have a fluid, self-gravitating fluid, and there's a differential equation of the pressure. Consult the clock again. Perfect. So this is what we have to solve. And at some point I'm going to hand this off to you guys, but since we're on a roll here, let's just keep going. And we're gonna come back to these limiting cases here. Okay, so now we certainly have spherical symmetry. So spherical symmetry, we've assumed it. So we have P is just a function of R in spherical coordinates, radial distance. So we need this del squared operator. Del squared P. Now you can do two things, and maybe we should derive this if we haven't derived it before. D squared P dr squared plus 2 over R dP dr. You can go ahead and do that. If you look this up in terms of spherical polar coordinates, you'll find the following expression. 1 over R squared, and then we'll have ddr d over dr R squared dP dr. This one looks simpler actually, this one. On the other hand, for a problem where the constant where the right side is a constant, you can make very short work of this problem, okay? On the other hand, suppose you wanted to derive this thing. And make sure I got that right before we go on, but I think so. Because this is roughly where I think we'll leave it. Yeah. If you wanted to derive this first one here, how would you do that? You know, we're looking at derive for r equals root x1 squared plus x2 squared plus x3 squared del squared equals b squared dx1 squared b squared dx2 squared dx3 squared. So it's actually not that long, because once you do it for one, you know, of these indices, you see how you add them up, and you'll obtain this thing here. So yeah, this would be a good exercise to do, and then you can quickly see that it actually takes this form as well. So I'm going to leave you guys with this problem, because with this form, because this is a constant, it's just a few lines, and you can integrate this thing up. What you're going to find is, find P of R equals, you know, it's going to look something, it's going to have that form, okay, with a piece of 0, but in this case, the piece of 0 is not at the surface, this is in the center. So you're going to integrate this up, you're going to find P of R, and then again, in fact, you'll already have had it before you get the final answer, you know, dP dr equals question mark, okay? So you have these two things. It's going to be quadratic, okay, I'll give away the suspense. But you're going to have this, and it's not going to look just like minus rho times g, okay? But it actually is in there. So note, g for a fluid is, you know, at the surface, g is g m over r squared. So this g is going to be g over r squared. What's your mass going to be? Your mass is going to be density 4/3 pi r cubed. And that should pan out. When all is said and done, that'll be, unless I made a mistake here, g m over r squared. Yeah, at the surface, at r equals r. So anyway, that's a pretty satisfying problem to do, non-trivial, and with a, you know, with a special check there in the limiting case, that'll be good as well. That's at the surface. Okay, checking the time once more. I think this is a good place to call it a day. Indeed it is. So there you have it. That's our discussion of hydrostatics. And if you want a little more, like I said, your undergrad book probably has a bunch of interesting buoyancy type of problems. And I gave a couple, and you guys work through this. I think you'll enjoy that too. Good. See you guys next time.